Hello everyone. Today we are starting with the new topic of wave optics, that is about interference of waves. If you remember our first introductory class, and what are the topics that we discussed are that first is the wave theory supported by Huygens. Then we discussed about Huygens principle and what it says that every point on a wavefront acts as a secondary source of new wavefront in forward direction. And we studied how waves actually propagate in free space. Then we studied about reflection of waves using Huygens principle, refraction of waves using Huygens principle. Alright, today we'll start with another phenomena of wave, and that is interference of waves. Interference. And how we study interference is that if we consider any random arbitrary wave propagating in particular direction, and we see that this is transverse wave, it travels in the form of crest and trough and having maximum amplitude of E1. Now, if we consider another wave that has maximum amplitude or maximum displacement E2, but what we see is that second wave has exact same location of crest and trough as the previous one. That means these two waves have exact location or coincidence of crest and trough. Their crest and troughs happen together. Their crest and trough take place together. So when these two waves are added, their net displacement will be added. So the resultant displacement of these two waves will be represented by this green wave, and that is E1 plus E2. Why their simple amplitudes are added? Because they have same locations for crest and trough. Such interference, let's say if this is 2 volt, this is 5 volt. Let's say E1 is 5 volt since it is larger in magnitude. E2 is 2 volt. When they are added, when their crest coincide, their net amplitude will be plus 5 plus 2. So net amplitude will be 7. When their trough coincide, trough is the negative amplitude. So this red one is minus 5. This is minus 5. This is minus 2. So net displacement will be minus 7. Here it is minus 7. Here this is plus 7. Again when their crest coincide, plus 7. When their trough coincide, minus 7. So this is how they get this green wave, and that is the redistribution or the addition of two individual waves, crest and trough. Such interferences are called constructive interferences. Constructive in the sense their crest and troughs coincide and they are simply added. Alright, if we have waves like this where crest of one wave coincides with the trough of the other. See, here this crest of one wave coincides with the trough of the other. So now if we continue with our data, that if E1 is plus 5, that is crest, E2 is let's say minus 2 with trough, so the net displacement will be 5 minus 2. So net displacement will be smaller. See, such interferences are called destructive interferences. Destructive when crest of one wave coincide with the trough of the other. So the next net displacement will also be E1 plus E2, but net displacement will be lesser because if one is positive, the other is negative. Conversely, at this location, this red signal has trough, that is minus 5, but this blue signal carries crest of plus 2. So the net displacement will be minus 5 plus 2 is minus 3. Again plus 3, minus 3, plus 3, like this. So to summarize all this, when two waves crest and trough coincide, the net displacement will be addition. Algebraic addition, net displacement will be greater. It is called constructive interference. When the crest of one coincide with the trough of the other, such interferences are called destructive interferences. Net displacement will be smaller. Okay, so these are two types of interferences that we have studied, and this is the notifications that we have used. All right, another view of observing the same phenomena is this. These are two sources carrying waves in the form of crest and trough, but now we'll observe these interferences from the top view. From the top view, that means now we are observing waves like this, like distribution of waves on water. And what is our notification? Let's say this blue are crest, all these blue circles are crest, while these yellowish ones are trough. So blue represent crest, this is trough. Let's see again. This represents waves transverse waves from the top view. When we release a stone in water surface, we get waves generated like this. Correct? This is a redistribution. Now what we see, Uh, Blues are crest, yellows are trough. And what we know from this introduction is that when their crest coincide, it is constructive. When one crest, one trough coincide, it is destructive. Now observe here. When two circles or two arcs of same color coincide, it should be constructive because blue is crest, yellow is trough, crest, trough like this. Now observe these points. Here two blue coincide. That means crest of one wave coincide with the crest of the other. Crest coincide should be constructive. See here. Trough of one, trough of the other coincide, constructive. That means two arcs of same color coincide. There are either two crests or two troughs. They should be added. So this entire intersection should give high amplitude, that is constructive interference. Similarly, when two arcs of opposite color coincide like this, two arcs of opposite color, see here, okay, then we will have destructive interference like this. See at this point, crest of one coincide with the trough of the other. Here arcs of different color, arcs of different color. So this entire intersection should give us interference of one crest, the other trough should give us destructive interference. Again, try to find out few more. See here, intersection of two same color, that means these are all intersection of two crest, intersection of two troughs, crest trough. That means this should also give us constructive. That means this should be maximum intensity because this is constructive. Here one interference of crest and trough, one crest and trough. This should be minimum because it is destructive. Try to find out one more of destructive interference. Okay, where intersections of will have intersection of two different colors. Like see here, one crest, one trough. Again, continue. Crest trough. We have intersection of two different colors. So this should also give us minima. See, the intersection of two different colors. Okay, here also. This should give us intersection of same color. So it is maxima. Like this. So when these two waves coincide, we get alternate maxima, minima, maxima, minimas due to their constructive and destructive interferences. And the resultant pattern will give us alternate bands of bright and dark fringes. We'll use the word fringe. Okay, bright fringe takes place when two intersections of crest or trough, that means intersection of two arcs of same color. See, dark take place when intersection of two different colors, that is one crest, one trough. Here two crest, two trough. Here one crest, one trough, intersection of two different colors. So this how what we need to show from this figure is that all right, there is instructive and constructive interferences, but when there are interferences of two waves like this, when they superimpose, what we get are alternate bands of bright and dark. All bright bands are due to constructive interference, all dark bands are due to destructive interference. And these are the notifications that we have used. Okay, so this phenomenon of one wave interfering with another and resulting redistribution of energy in the space around two sources is called interference. So you can write down this definition in your reference book. That is the definition of interference. Two types of interferences: constructive, destructive. Constructive interference takes place when we have interference of two crest or trough. Destructive when one crest coincides with the trough of the other and vice versa. Destructive interference causes dark fringes. Constructive interference causes bright fringes on the screen. Okay, so this slide is about the introduction of interference that we'll be studying in today's class, and we'll have more discussions on this. Okay, now what this particular theory says. See, now we'll discuss that same topic analytically, mathematically. That means if one wave is a sine omega t, normal wave equation, the other wave would be b sine omega t plus phi, where this phi indicates phase difference between two waves. Now, due to superposition, these two are added. See, these are the notifications. Two waves with same speed, wavelength, frequency. This is what I was talking about. Phase difference between two waves. These are basic terminologies related to wave that we have studied in 11th standard. Omega is the angular frequency. E1, E2 are the displacements. A, B are amplitudes, like this. When these two are added, due to superposition, we get E1 plus E2. Add them. E1 is A sine omega t. E2 is B sine omega t plus phi. Now we'll use one identity here. You can write down this step in your notebook also. Let's see. A sine omega t as it is plus B. We'll expand this. Sine omega t plus phi can be expanded as B as it is. This sine omega t plus phi can be expanded as sine omega t cos phi plus cos omega t sine phi. This is the expansion of sine omega t plus phi. Now what we'll do, we'll take them common. See, from these two terms we can take sine omega t common, and in the bracket we'll have a plus b cos phi. See, sine omega t is taken as common, and what we'll have a plus b cos phi. Similarly, the other term is b cos omega t sine phi. Okay, so you can write down this term in your notebook that this is the expansion. If you're comfortable with the trigonometric identities, you need to go ahead directly, then that is also okay. Okay, but these are for the inclusion of the mathematical identities that we have used, and sine omega t plus phi can be expanded as sine omega t cos phi plus cos omega t sine phi. Then we have taken sine omega t common, and the remaining term is here. Okay, now if we continue with this, then sine omega t, this entire term a plus b cos phi is taken as capital A cos theta. See, and this b sine phi is taken as capital A sine theta, so that this first term will be a cos theta sine omega t, and this is represented as a sine theta cos omega t. After this substitution, this equation will look like this. See, this entire bracket is taken as a cos theta sine omega t as it is, plus b sine theta, b sine phi is taken as a sine theta cos omega t as it is. The reason for taking this substitution is now we get a common, and we'll have that exact identity that we were using earlier. Sine omega t cos theta plus cos omega t sine theta. So this can be expanded. This bracket can be written as sine omega t plus theta. All right. This is the reason for taking these substitutions, so that this entire identity will be a standard one. Sine omega t cos plus cos omega t sine, and the resultant amplitude will be a sine omega t plus theta. These are all mathematical steps you can cover in your reference books. So you can pause this video right now. You can write down all these mathematical identities if you want, and then you can move ahead. Okay, so after writing this, we get E equal to a sine omega t plus theta. Now what is A? Capital A. It is the amplitude of the resultant wave. See, make sure this is wave 1, this is wave 2. When these two are added, the resultant wave will look like this. So this is the resultant after superposition of two waves. So this capital A is the amplitude of the resultant. And to obtain capital A, what we have done, we have squared and added these two identities. See, we have squared and added. When you square RHS, we'll get a square cos square theta plus a square sin square theta. Cos square plus sin square is 1. So one side is a square. The other side, a plus b cos phi whole square, b sin phi whole square, and we get this. Since LHS was a square, square is removed, we get the under root of a square plus b square plus 2ab cos phi. So this represents the amplitude of the resultant wave. Similarly, this theta represents the phase angle of the resultant wave. And to obtain theta, we have taken sine theta upon cos theta. So we get in terms of tan theta. 2 upon 1. So we'll get b sine phi upon a plus b cos phi. So this theta is the phase angle of the resultant wave. Correct? So this is pure mathematical analysis of interferences. When they are added, we apply superposition, apply some trigonometric identities, and we get resultant wave as a sine omega t plus theta, where capital A is the amplitude of the resultant wave. See, this is all written, and theta is the phase difference of the resultant wave. Okay, now moving on, we'll analyze these equations further, and this capital A is root a square plus b square plus 2ab cos phi. This is very straightforward calculation. You square these two terms and add them, you'll get this. Now, this is the amplitude of the resultant wave. This is simply the vector form, no need to cover this. Now, this is the same equation that we are talking about, amplitude of the resultant wave. When we talk about intensities of the resultant wave, then what we know, intensity is proportional to the square of amplitude. I is proportional to a square. Remember in 11th standard we obtained that intensity of a wave is ka square, where k is the constant. So intensity is proportional to the square of amplitude. So you square these terms, you get intensity. See, so when you square them, you take out this root and we get simply a square plus b square plus 2ab cos phi. Okay, so this I is the intensity of the resultant wave. Correct? Now, this intensity of resultant wave will be maximum. Remember the first slide. Constructive interferences will give bright fringes. Destructive interferences will give dark fringes. So this intensity will be maximum. Fringe or band will be bright if this intensity is maximum. So if constructive interference takes place, this intensity will be maximum. This is maximum when cos is maximum. Cos has maximum value of 1, correct? And cos becomes 1 when phi is 0, 2 pi, 4 pi, 6 pi, etc. See, cos 0 is 1, cos 2 pi is 1, cos 4 pi is 1, like this. So in general, cos phi is maximum, and in turn, intensity is maximum when phase angle is integer multiple of 2 pi. See, it is 2n pi, where n is taken as 0, 1, 2, 3. You can try n is equal to 0, first value, n equal to 1, second value, n equal to 2, third value, like this. Correct? So this phi is the phase difference between two waves is integer multiple of 2 pi. Then cos phi will be 1, intensity will be maximum, and what we get on the screen is the constructive interference. Phi is to n pi. Similarly, we can also discuss path difference together. Achha, this phase phi is phase difference. Remember the first video lecture what we discussed is that phase difference is 2 pi by lambda into path difference. This is also the equation that we have carried from the 11th standard. Now this phase difference for constructive is 2n pi. So this phase difference is 2n pi is equal to 2 pi by lambda. Path difference is denoted with delta. So 2 pi cancel. So what is path difference? N lambda. See, correct? So this is phase difference measured in terms of radians for constructive interference. This is path difference measured in terms of meters for constructive interference. Generally, we discuss path difference in the next theory, but in this slide, we discovered along with the phase differences, and this is the same equation. We have made path difference the subject. So we get lambda upon 2 pi phase difference is 2n pi, 2 pi cancel. So we get path difference for constructive as n lambda. N is 0, 1, 2, and so on. Okay, similarly, condition for destructive interference. Destructive when intensity is minimum, we get dark band on the screen, so cos phi should be minimum. Cos is minimum when it is -1, and cos is -1 at pi, because cos pi is -1, 3 pi, 5 pi, 7 pi, like this. These are all values of phi at which cos is -1. So in general, it is 2n plus 1 pi, where n is equal to 0, 1, 2, 3, and so on. Try to substitute the values. N equal to 0 pi, n equal to 1, 3 pi, n equal to 2, 5 pi, like this. So again, this phi is phase difference between two waves for minimum intensity or destructive interference. Again, this is phase difference. What would be path difference? Path difference. What was the equation? Phase difference is 2 pi by lambda into path difference. So make path difference the subject. So we'll get lambda upon 2 pi into phase difference. See? Lambda upon 2 pi into phase difference. Phase difference for destructive is 2n plus 1 pi. Simplify. We get 2 pi cancelled, pi cancelled, and we get the equation. See, pi cancelled, we get 2n plus 1 lambda by 2. Okay, so this is the path difference measured in meters for destructive interference, or phase difference measured in radians for destructive interference. Okay, now This particular equation shows the maximum intensity. Intensity is maximum when cos is 1. If this term is 1, then we get a square plus b square plus 2ab, that is equal to a plus b and whole square. So similarly, it is minimum when this cos phi is minus 1. See, for destructive, if it is minus 1, we get a square plus b square minus 2ab. It is proportional to a minus b whole square. Okay, so this slide includes the conditions for maximum intensity or constructive interference. Phase difference is 2 n pi, or n lambda is the path difference, and condition for destructive interference, that is 2n plus 1 pi or 2n plus 1 lambda by 2 for the path difference of destructive interference. Okay, so these conditions are very important to understand path difference for constructive and destructive interferences. Okay, now moving on, when we compare their intensities, remember maximum intensity is a plus b the whole square because cos phi is 1. Minimum intensity a minus b whole square because cos phi is minus 1. So when we take the ratio, it is a plus b the whole square upon a minus b the whole square. Simplifying this, or we can take b common, we get a upon b plus 1 whole square, a upon b minus 1 whole square, and a upon b is chosen as a constant r, where this r is the ratio of a upon b. And remember, a is the amplitude of the first wave, b is the amplitude of the other wave. So this r is a upon b, that is the ratio of their amplitudes. So this particular equation shows the ratio of maximum and minimum intensities on the screen. Again, I'm revising this point. Maximum intensity takes place when two crest or two trough coincide due to constructive interference. Minimum intensity on the screen takes place when one crest and one trough coincide due to destructive interference. And the ratio of maximum and minimum intensities on the screen is r plus 1 whole square upon r minus 1 whole square, where r is the ratio of amplitudes of individual waves. Okay. Now, one more thing, this particular point you can write down in your references note, because this will be useful in numericals only. That is relation of intensities and amplitude and the width of the slit. We'll come to this width of the slit in a while, but right now we simply note this down points, that is intensity is proportional to the square of amplitude. We know it is proportional to root of width. Amplitude is proportional to the root of width of the slit. And if you take the ratio I1 upon I2, A1 upon A2 whole square, or W1 upon W2, because when we square this term, we can write A square is proportional to width of the slit. So in general, we can write I is proportional to A square and A square is proportional to the width of the slit. So see, you at this point of this video lecture, simply write down this relation. You know what is intensity of the resultant wave, amplitude of individual waves. Now we'll come to this point. What do we mean by the width of the slit? And for this we have to study a very important topic of this lecture, that is called Young's double slit experiment. We'll call it YDSE. Young's double slit experiment. See, in this topic we'll discuss what is a slit. And a slit is a narrow opening in a given wire or in a given plane. So this is the source that will generate waves. This indicates two narrow openings, that is double slit in a width in a plane. So this is the width of slit. This is the width of slit that was mentioned in the previous slide. This width is mentioned in the previous slide. That means this intensity is proportional to the square of the amplitude of the wave and is proportional to the width. That means if this width is made larger, this opening is made larger, intensity on the screen increases. If these widths are made larger, intensity on the screen increases. If we make narrow slit, narrow opening, intensity decreases. So this is what we meant by width of slit in our previous topic. Okay. Now in this particular slide, we have to study what is Young's double slit experiment, and this is mention of alternate bright and dark fringes that we covered in the first slide of today's class. First slide, remember that alternate maxima and minima coincided, and we draw alternate maximum and minimum bands. So this alternate maxima and minima looks like this on screen. These are all bright fringes taking place due to constructive interference, These are all dark fringes taking place due to destructive interferences. And how do they? What is the experimental setup of IDSE? Is this? We have one source. It is made to pass through two narrow openings, two slits, S1 and S2. Waves after passing through the slit are made to fall on a screen. See, these are two slits. Waves are allowed to pass through the slit, this narrow opening, and they are allowed to fall on a screen that is placed at some distance away. Okay, so this is slit, two slits of width W, location S1 and S2. The separation between two slit is small d. The distance between slit and screen, this is screen, is capital D. Okay, notation. Small d is the separation between two slits. Capital D is the distance between slit and the screen. This is D, this is the center location O. Center to the point at which all these rays fall is Y. Okay, distance from the center at which all these rays fall is Y. This is D, so this is D by 2, D by 2. Clear? So this is the experimental setup and the basic notifications. That is the distance between slit to screen, separation between two slits, distance from the mid center of the screen to the point, etc. Okay. Now if we go by the mathematics, then what we know that these two waves, this is first wave. Remember, this is drawn as ray, but this is actually the wave traveling towards the screen. This is another wave traveling. And what we know that this wave from the S2 travels a little extra distance to reach P. Yes, because P, point on screen, is closer to S1, while point on screen P is slightly away from the S2. So this second wave has to travel slightly extra distance to reach P. So the extra distance traveled, that means there is some path difference. Path difference because 2 travels some extra distance. So S2P is greater distance. S1P is slightly shorter distance. So the path difference delta is S2P minus S1P. Clear? Very important part of this theory. S2P is the distance from second slit to the point on screen. S1P is the distance from first slit to the point on the screen. Since this is slightly extra distance traveled, so the path difference is S2P, longer distance minus shorter distance. All right. To further elaborate, we'll consider this triangle. This is S2P, this is capital D, and this vertical part is, see, make sure this is Y and this is D by 2. So the height of this triangle is Y plus D by 2. All right. See, we are considering this triangle. This is right angle. So this is hypotenuse S2P. Base of this right angle is capital D. And the side of that of this right angle triangle is, this is Y plus D by 2. Okay, so if you apply Pythagoras, this hypotenuse square, let's write it here. S2P square is equal to, S2P square is equal to D square plus the height is Y plus D by 2, Y plus D by 2 whole square. Similarly, clear? Okay, make sure this is very important. Okay, write down this in your notebook. This S2P is the hypotenuse square is equal to capital D square plus Y plus D by 2 whole square. Okay, similarly, we will take another triangle. Now we'll consider this. S1P is the hypotenuse. This is the base, that is capital D, and now only this is height. So this height is, we subtract D by 2 from Y. So this distance is Y minus D by 2. All right. See, this is capital D whole square. This entire distance is Y, but out of this Y, if we subtract D by 2, we get this distance. So again, this is right angle. Apply hypotenuse, Pythagoras triangle. So there is hypotenuse square, S1P square is equal to capital D square plus Y minus D by 2 whole square. Correct? So in short, what we get is S2P square is, say, remember S2P is this, you must have written in your notebook, is D square plus Y plus D by 2 whole square. Similarly, S1P square is mentioned on the screen. capital D square plus y minus d by 2 whole square. Now when we subtract this two, what we get? When we subtract, s2p square minus s1p square is capital D square plus, we can expand y plus d by 2 whole square as y square plus 2y into d by 2 is yd plus d by 2 whole square, d square by 4. Okay, d square plus y plus d by 2 whole square is y square plus d square by 4 plus 2y d by 2, 2 to cut. Similarly, this is s2p whole square minus s1p whole square is capital D square. Again y minus d by 2 whole square is y square plus d square by 4 minus 2y d by 2 is minus y. All right. So when we subtract this, what we see is that d square minus d square cancel. Y square minus y square cancel. D square by 4 minus d square by 4 cancel. What we get? Yd minus minus yd. So that means s2p square minus s1p square is 2yd. Correct? Yd minus minus yd. Clear? So this is important. Again, I want you to write down all these steps in your notebook, where you get s2p square from the term, s1p square from another triangle. You square them, subtract them. This is the simple mathematics and this cancellation of terms. You get s2p square minus s1p square is equal to 2yd. Clear? Write down this first in your notebook, then only move ahead, because we'll have lots of calculations based on this particular equation only. S2p square minus S1p square is 2y small d. This is the reason and the explanation of this term. Okay, after writing this down, we can move ahead, and these are the same terms. See, S2p square, S1p square, when we subtract them, you get 2yd. All right. When we again expand them, S2p square minus S1p square is factor. That is a square minus b square. A minus b, a plus b. Again, similarly, what we have shown, again, if we simply add them, S2p plus S1p, we'll get 2 capital D, and S2p minus S1p is the path difference. See, so this is delta. This can be shown again with simple calculation, like in the previous, just a moment before that we have discussed the subtraction. When we add them, you get 2 capital D and 2 yd is what we have obtained. So when you cancel 2, we get delta y small d upon capital D. Clear? Again, I'm telling you, no need to show all this intense mathematics in your theory part, because lots of mathematical steps are still left. Okay, whatever I have shown in this video class, or whatever the calculations we have discussed just now, is for your reference. In exam, you can simply write down this step subtraction. This you have to remember that this is from the triangles we have written, we have just discussed. Apply Pythagoras, subtract them, you get the equation. Okay, so this is the equation of path difference, that is y small d plus capital D. We are not yet done with this theory. We have to consider this path difference for bright fringes, that gives constructive, and dark fringes, that gives destructive interferences. See, now for the bright fringes, that is constructive interference, remember path difference is n lambda for constructive interferences. See, okay, so delta is y small d upon capital D, we have just discussed in the previous slide, and delta is equal to n lambda, we have discussed in the slide when we discussed that cos phi is 1 for maximum intensity. So cos phi is 1 for 0, 2 pi, 4 pi, etc. And in that slide we discussed that path difference is n lambda for the constructive. So we have simply compared two equations of delta. Okay, so if you go ahead, n can be 0, 1, 2, 3, etc. And what we get, you make y the subject, you get n lambda capital D upon small t. Very important equation. So this y is the distance from the center to the point on screen at which we will get maximas. So you will get maximas when you have n lambda capital D upon small d. That means when you make n equal to 0, first maxima is lambda capital D upon small d. You make n equal to 2, you get 2 lambda capital D upon small d. N equal to 3, 3 lambda capital D upon small d. You make n equal to 0, and it is 0. Y equal to 0, that means it is exactly in the center. See the previous slide. See, this is y. This y what we have obtained is n lambda capital D upon small d for the bright fringes. So n is 0, that 0 is the exact center of the screen. So at this point you get bright fringe. Next bright will be when you place n equal to 1. So next bright will be lambda capital D upon small d. N equal to 2. Another bright will be at 2 lambda capital D upon small d distances. These are all distances. This is first maxima. Next maxima will be lambda capital D upon small d away. Another maxima will be 2 lambda capital D upon small d away. Similarly, in the below sections also. So this particular term that we have obtained, this equation, y is the distance from the center at which we get maximas. Distance from the center at which we get maximas. So we get maximas at 0, lambda capital D upon small d, 2 lambda capital D upon small d, like this. Okay. Similarly, if we consider dark fringes. For dark fringes, path difference is 2n plus 1 lambda by 2, where n can be 0, 1, 2, 3, and so on. Now, if you simply substitute or compare and make y the subject, so you get 2n plus 1 lambda by 2 capital D upon small d. Okay, so this is the condition or the distance at which we get minimas. Dark fringes, destructive interference. Substitute n equal to 0. When n equal to 0, you get lambda capital D upon 2d. N equal to 1. N equal to 1, so this is 3. 3 by 3 lambda capital D upon 2d. N equal to 2. So this is 5 lambda capital D upon 2d, like this. So these are the positions at which we get minimas. Okay. Now also, what is the separation between two consecutive maximas and the separation between two consecutive minimas? See here, expression for dark fringe width, that is separation between two consecutive minima. Expression for bright fringe, that means the separation between two consecutive maxima. Try this. What is the distance between first maxima and second maxima? First bright fringe and second bright fringe. Y1 minus Y0. It is lambda capital D upon small d. Similarly, what is the difference between first bright and second bright fringe? See, 2 lambda capital D upon small d minus lambda capital D upon small d. These are same terms. See, so again the subtraction of y2 and y1, y2 minus y1, is again lambda capital D upon small d. That means separation between two consecutive bright is lambda capital D upon small d. Similarly, check separation between two consecutive minima. See, check this. Lambda capital D upon 2d is common. When you subtract this 2, we get 3 minus 1 in the bracket. This is 2, 2 cut. What is the separation between two consecutive minima? Y capital D upon small d. Try any of these two. See, this 2. Again, distance between second dark fringe and first dark fringe. Two consecutive minima. Any two consecutive minima. Again, lambda capital D upon 2d common. In the bracket, what we get? 5 minus 3. 2, 2. Again, lambda capital D upon small d. Okay. So this shows the distance between two consecutive minima. This shows the distance between two consecutive maxima on screen. Distance between two consecutive dark fringes. Distance between two consecutive bright fringes. And it is same. Lambda capital D upon small d. So they are equidistances. They are equally spaced on the screen. Correct? And we can show this with the variations also. See, these are all maxima. These are all bright fringes. These are all dark fringes. Remember, at what locations we get bright fringes? You must have written in your class book. This is first bright. Second bright is lambda capital D upon small d. Next bright, 2 lambda capital D upon small d. Remember, these are the distances from the center. 3 lambda capital D upon small d, like this. At what point we get minimas? We get minima at lambda capital D upon 2d. This minima, 3 lambda capital D upon 2d. This minima, 5 lambda capital D upon 2d. So these are the distances from the center at which we get first maxima, second maxima, third maxima, like this. Again, conditions for first minima, second minima, third minima, like this. Okay, so that same calculation have been placed on the graph, and these are basic equations of maximum A plus B whole square for the maxima. But if two sources have same intensity, See, original equation of maximum intensity was A plus B the whole square. A and B are amplitudes of two different waves. But if both the waves have same amplitude, then we can simply write A plus A whole square, that is 4A square. So all maximum bright intensities will have equal amplitude of 4A square if they have two sources. If we study interference of three sources, we will get all three sources A plus B plus C whole square. If all these waves have same amplitude, then A plus A whole square, we get 3A plus whole square, that is 9A square. Okay, so this 4A square is when we have two waves interfering. If we have three waves interfering, 9A square. If we have four waves interfering, 6A square. So I would suggest you to remember that maximum intensity is proportional to NA square, where N is the number of waves of equal amplitude. N is the number of waves of equal amplitude. They must have same amplitude. So if, since in this discussion we have discussed interference of two waves only, we get maximum of 4A square, Na the whole square, Na the whole square. Correct? So this is how we get maximum intensities terms. Minimum intensities are zero if they have equal bright fringes. Then it would be, remember, minimum intensities equation was A minus B whole square. If they have same brightness, minimum is zero. All dark fringes have zero intensity. Okay, and these are the conditions for all this what we have discussed, is that two sources should be coherent. That means they should have same frequency and wavelength and phi. Two interference wave must have same plane of polarization, matlab both should be transverse or longitudinal, traveling in the same plane. They should be very close to each other, so because at large distance we have sufficient width of the screen, lambda capital D upon small d we have discussed. And the sources should be monochromatic, that means this wavelength should be single. If you use polychromatic like the bulb that carries multiple colors, then it is not possible or not easy to observe all these dark and bright fringes separately. So we would suggest that we have the sources that we study interference should be monochromatic. They should carry only single wavelength. Otherwise fringes are not possible to observe them separately. Their colors and wavelengths will overlap. Okay, and the two waves must have same amplitude for better contrast. Why better contrast? Because they have same amplitude, that means maximum intensity is 4A square, minimum 0. So we'll have large separation between maximum values and minimum values, so we can observe them very sharply and very distinctly on the screen. Okay, so there are the obvious conditions. The two sources must have same frequency, so coherent, they should be traveling in the same direction, they should be close to each other, they should have single wavelength, else it is not possible to see them separately. If they are single color, they should have same amplitude for better contrast of the fringes. Okay, so these are the conditions for the sustained interferences. So this concludes our topic of interference of waves. What we have studied is the types of interference: constructive, destructive. Then we studied conditions for maxima and minima, that is amplitude is maximum, intensity is maximum when path difference is n lambda. Intensity is minimum when path difference is 2n plus 1 lambda by 2. Then we studied Young's double slit experiment, lots of mathematics, and then you have to obtain the conditions for maximum brightness, lambda capital D upon small d, minimum brightness, lambda capital D upon 2d, for, and then separation between two consecutive maximas, minimas, their intensity patterns, and the conditions to obtain all these interferences. Correct? So these are all numericals. These are all the topics of the interference of waves, or rather Young's double slit experiment. In the next class, we'll discuss numericals based on Young's double slit experiment.